It's my great pleasure to introduce Susan Niefield, who will tell us about Cartesian closed double categories. Take it away.
And I have a little something blocking part of my title. Do you see that, or am I just seeing
No,
that?
we don't see that at all.
Perfect. Okay, so to start with, no, it's not. They're not going. There we go. This talk is in memory of Marta Bunga. When I started preparing this talk, or right after Marta passed away, I realized, and hadn't realized this before, that some things that Marta and I did led into my interest in double categories. And I hadn't realized this before because she didn't do anything much with double categories. Anyway, I've included a couple pictures. Here's a picture of a trip several of us took after a category theory meeting in Switzerland up to the Jungfrau, up to the city of Mürren. And here's a picture of a few of us, Marta, McLean, and me, in the audience at the 1994 meeting in Tours. Anyway, so here's what led to my interest in double categories. So first of all, back in 1978, with a paper appearing in 82 in my thesis, I talked about exponentiability. And in particular, I showed that the inclusion of first topological spaces, the inclusion of a subspace is exponential if and only if it's locally closed. Then when I was a postdoc in Halifax shortly thereafter, I extended this to locales and toposes. And then quite a bit later, but Marta wrote to me, and when I was preparing for a sabbatical in Montreal in the winter of 1998, Marta wrote that we, and the we was her and Jonathan Funk, were interested in things I'd done with exponentiability and locally closed. So she was interested in these results for some other situations. In particular, we used exponentiability of locally closed subcategories to show that the category UFL over B, such unique factorization liftings over a category, is a topos if B satisfies. She was hoping we could prove this for all B, but we needed some condition called interval gluing on the base. Anyway, while I was there, I learned about a note Street had. So we were talking about exponentiability in CAT, which was well known. People attribute it to Condorcet, but it really came from Giraud about 10 years before that, and people talk about the Giraud-Condorcet condition. In any case, Street had a note, which he never published, but it's available, which used Benabou's equivalence between lax normal functors from a category B to the bicategory of profunctors, equivalence between that and categories over B, to show that Y is exponential in CAT if and only if it satisfies what I'll call FL, but the factorization lifting property, which is also known as the Giraud-Condorcet condition. Anyway, the result was well known, but not using this equivalence as far as I know. And then later, once I saw this equivalence, I started applying it to many other categories to get some exponentiability results. And I was giving a talk on some of this when Bob Perret said, oh, you're doing double categories there. And actually, at first, I didn't see it because I didn't know much about double categories. And then this was around 2009, I think it was, even though that paper that I'll have in my references at the end came out later. Anyway, Jeff Cretwell explained to me the next fall, I think it was, what Bob was talking about. Anyway, so I took off on that with these locally closed inclusions, and I started encoding this in double categories in something I called a gluing category, a gluing double category, and that was because it generalized the Martin-Raith gluing that's used in toposes and locales. So I had a single theorem from which I could construct exponentials of locally closed inclusions for topological spaces, locales, toposes, categories, and posets all from a general theorem about double categories. Okay, so what I'm interested in today doesn't really have much to do with that, except it really is a generalization of something I did for gluing categories, or it's related to it or an extension of it. So if one's interested in Cartesian closed double categories, let's back up. There are two approaches to Cartesian closed one categories. One, you can do it object-wise. You can just categories Cartesian closed if and only if crossing with an object has a right adjoint for every y. Okay. The alternate approach is that if you have a bifunctor from C up, cross C into C, such that there's a natural bijection between morphisms from X cross Y to Z and C, and morphisms from X to, I'm just calling it Y bracket Z. It's easier to write for a bifunctor here. Usually it's Z to Y. Anyway, these are equivalent for ordinary categories, but it turns out I've been considering the object-wise approach for double categories. And if you now consider a bifunctor approach, it turns out they're not equivalent. Okay. So anyway, here's what I'm going to do. First, I'll talk about double categories and a few of the examples I'm interested in. And then lax double functors and adjoints. And then, so those first two are just reviewing the notation and examples I'm interested in. Then Cartesian closed categories. And I'll apply that to the initial examples I'll mention. And then I'll talk about more examples, the ones that are all these so-called gluing categories. Okay. So I can't see my headings because something's covering it. I don't know how to hide this. I guess I can't. Anyway, a double category is, for the purpose of this talk, is a pseudo-internal category in CAT. So this is the same diagram you've seen. I follow the conventions that Perret follows. In particular, like everyone, the objects of D0 are called the objects of D. My horizontal morphisms are the morphisms of D0. My vertical morphisms are the objects of D1. I'll call those vertical morphisms. And the cells, a cell from an object V from X0 to X of T to X of S to X of T in D1 to Y sub to W from Y sub S to Y sub T is called a cell of D. Okay, so examples. So the first few examples I'm going to be interested in, there's the double category of span, double category span. The objects are sets, the horizontal morphisms are functions, the vertical morphisms are spans, and the cells, a span from V, sorry, a morphism from a span with vertex V to a span with vertex W consists of a function from X of S to X of T, another function from V to W, and one from X of T to Y sub T, making that diagram commute. And of course, you can do this. For composition, you need to use pullbacks, so you can do this with in any category with pullbacks. Similarly, one can talk about rel. The objects are sets. The horizontal morphisms are functions. The vertical morphisms are relations. And you have a diagram from a relation R to relation S, which consists of a function F sub S and a function F sub T, with the property that if X sub S, X sub T is in R, then F of X sub S, F of X sub T is in S. And then there's a third example I'll be interested in initially, which this is the third time we've seen this this week. The objects, it's the double category of squares. The objects are sets. The horizontal morphisms are functions, and so are the vertical morphisms, and the the cells are commutative diagrams. Okay, and I'll just note, because this will come up later, that square sub 1 is the category of sets to an arrow, the arrow category, okay, which is a topos, by the way. Okay, lax functors. So a lax functor f from D to E consists of functors f0 from D0 to E0 and f1 from D1 to E1 compatible with S of T, compatible with S and T. And cells, there's a cell that compares the vertical identity for every x on f of x naught to f1 of the vertical identity on x. And there's also a cell for every composable pair W and V from F1 of V composed with F1 of W composed with F1 of V into F1 of W composed with V. And they satisfy naturality and coherence conditions. Oplex and pseudo-functors are defined with the cells in, well, for oplex in the opposite direction and invertible for pseudo-functors. And I'll let lax DBL denote the category, the two category of double functors, sorry, double categories and lax functors and appropriate two cells. Okay. So next, here's a lemma that comes from a Grandis Perret paper from 2004 that we'll use. So it says the following are equivalent for a lax functor f from D to E, which has functors G0 in the opposite direction from E0 to D0, and G1 from E1 to D1 compatible with S and T. So we have the following are equivalent. G is lax and F is right adjoint to G in the category of lax double functors. Sorry, lax categories and lax double functors. F0 is left adjoint to G0, F1 is left adjoint to G1, and G is lax, or the same thing, and F is oplax. So it's a characterization, the first condition, if you'd like, of adjoints in, adjoints in lax double. Okay. So why am I interested in lax double is even in the cases where one is looking at products in the category, in the two category whose morphisms are pseudo functors, the right adjoint, so the left adjoint crossing with something tends to be pseudo. Even in those categories, the right adjoints aren't, they're only lax. Okay, so that's why I'm interested in adjunctions in this category. Okay, so let me remind you of a definition from, it appears in the 2018 thesis by Alafieri, and it says a double category is, now she calls it pre-Cartesian, I'm going to call it lax Cartesian. A double category D is lax Cartesian if the diagonal functor from D to D cross D and the functor which takes D to the unique one object double category, if these have right adjoints, which are denoted by product and one. We just need product, but I'm just working with these lax Cartesian categories. Okay, so definitions. So first, and I'm going to drop, I'm putting the word lax in because everything in sight's going to be lax, but I will drop saying lax eventually. So a lax Cartesian double category D is lax Cartesian closed if there is a lax functor from D opt cross D into D, inducing Cartesian closed structures on D0 and D1. The next definition is an object Y is lax exponentiable in D if the lax functor D cross Y from D to D exists and has a right adjoint in lax double. So the only objects of D1 that have to be exponentiable here for this definition are the identity on Y, those, okay? And a lax Cartesian double category D I'll call object-wise Lax Cartesian closed if every object of y is Lax exponential in D. Okay. And notice that modulo three, in general, one usually implies three. The only thing one has to worry about is you could have both of these adjoints and they can be compatible. I don't have an example of a situation like that where you don't have the no, I think that's fine. Anyway, one tends to imply three. We'll see that three is weaker than one. So you can have every object to be object-wise Cartesian closed, but not have a bifunctor. And also you can have D0 and D1 Cartesian closed, but not compatible with S and T. So that doesn't even fit into this. The compatibility is something you want. Okay, any questions about these definitions? Is it okay?
I just have a quick question.
Yes.
When you write D op, are you opposite with the vertical structure or the horizontal structure?
I'm opping the horizontal.
Okay.
I believe. No, I'm see you in a second. No, just the horizontal. Yes.
Okay. Thank you.
Yeah. Okay. So let's look at rel first. Rel is Cartesian closed via this brackets bifunctor defined as follows. Well, because of compatibility with S and T, we need that the zero part of YZ has to be Z to the Y, because that's what it is in sets. And the one part, so given a relation S and a relation T, we'll define T to the S. So you can see here it's relative to it. The op is only relative to the horizontal. Yeah, we'll define T to the S as follows. We'll say that a function sigma sub S and a function sigma sub T is in the relation T to the S if such a diagram commutes. In other words, not commutes, if you have a cell. So in other words, if y sub s, y sub t is in S, then sigma sub s of y sub s, sigma sub t of y sub t is in T. Okay. And you can see that this is a Cartesian closed structure. We know it is in the horizontal direction. You just want to check it in the vertical direction. And you can show that given a diagram, so a morphism from R sub s cross R sub t, I said that wrong, R cross S into T, that will correspond to a morphism from R to T to the S, defined as follows. Given F sub S and F sub T, you define F sub S hat and F sub T hat in the usual way that you would for sets, and you can show that these diagrams are in bijective correspondence. Okay, so everything checks out. For span, it's similar. I won't write out the diagrams, but that's Cartesian closed. Y brackets YZ0 again is Z to the Y, and brackets VW1 for a V. That's a span from Y sub S to Y sub T, and W is span from Z sub S to Z sub T. W to the V is the set of spans, so it has to be a set. It's the set of spans of this form. Okay. And that's similar to rel. Okay, so here's an example, or a first counterexample. This category of squares, the double category of squares, is object-wise Cartesian closed, since, well, not since. It turns out to be object-wise Cartesian closed, and one can check that. And even though square sub 0 and square sub 1 are Cartesian closed, there's no bifunctor from square op cross square op into square, because if you look at in the arrow category, what do I have the right? Yeah, I do have the right thing. What v to the w, the source of v to the w, the source, if this were compatible with the source, you'd have to have that the source of that arrow of v to the w, so v to the w has to be z sub s to the y sub s. But if you look in the arrow category and you unravel what you have in that topos, you get that vw sub s is the set of commutative diagrams from v to w, and that's not compatible with the source. It is compatible with the target because that just sits over z sub t to the y sub t. Okay. So if you unravel what on the arrow, on the sets to the arrow, if you on the arrow category using Yoneda, what that is, this is what you get. Okay, so that's just an exercise. Okay, more examples. So these are the examples that I call gluing categories. So there's locales, the objects are locales. The horizontal maps are locale maps. The vertical morphisms are what are called left exact maps. So we have a v from a locale x sub s to a locale x sub t. It's finite meat preserving. So it preserves binary meats and the terminal object. And you have a cell precisely when you have that v followed by f sub t upper star is greater than or equal to v followed by, where am I going? F sub s upper star, followed by t is greater than or equal to w followed by f sub t upper star. So here the inequality is going in the opposite direction than you had for rel. So that's why I'm writing greater than 2. For topological spaces, this is the objects are topological spaces. The horizontal morphisms are continuous maps, horizontal arrows. The vertical arrows are left exact maps on the open set lattices. So a diagram like this, for a top, I'm putting an O on each thing here, open set lattice. And there's a cell precisely when f sub s upper star is greater than or equal to or contains v sub t upper star of w. And the upper stars here are just inverse images. Okay, cap. This is the usual double category of cat. The objects are small categories. The functors are, the horizontal maps are functors. The vertical maps are profunctors or distributors, if you like. And cells correspond to, from v to w, correspond to natural transformations from v to w of f sub s blank, f sub t blank. Posets is just kind of a restriction of this. The objects are posets. The horizontal maps are monotone or order preserving maps. The vertical morphisms are order ideals. So an order ideal from x sub s to x sub t is a subset of x sub s cross x sub t, which is downward closed in the first variable, upward closed in the second variable. And you have a cell precisely when f sub s cross f sub t of an ideal is contained in the ideal w. Okay, these 4 examples, actually topuses are a 5th, but each have an object 2, which is called the Sierpinski object, with the property that D1 is isomorphic to D0 over 2. And these, plus some other conditions, is what I call gluing categories. But this is the key, this D0, D1 isomorphic to D0 over 2 is what's key in getting the results. So the Sierpinski object in topological spaces is the usual Sierpinski space, 2 points with one of them open and one not. In locales, it's a 3-element locale, which is the open subsets of the Sierpinski space. And in posets, it's the usual 2-element, non-trivial 2-element poset, considered as a category in cat. Okay, so in couple of years ago, I was interested in exponentiability in D, and I was only thinking of it object-wise. And what I showed is that if you have one of these gluing categories, then Y is exponentiable in D, if and only if the functor blank cross Y from D to D is oblax and Y is exponentiable in D0. Okay. And the way the proof goes, I'm supposed to have Y exponentiable in D, then Y is exponential in D0, since crossing with Y has a right adjoint as an endofunctor of D0. And the converse holds, since crossing with Y on D1 corresponds to pulling back along the projection in D0 cross 2, which goes from the Sierpinski object cross Y into 2. And that's exponential in Y because when you go from a slice to the category, crossing with anything that's exponential in the category, in this case D0, is exponential. In fact, pulling back along anything preserves exponentiability. So that's how that went. So corollary, you get that Y is exponential in top if and only if O of Y is locally compact in a continuous lattice, that is, that's at locally compact as a locale. And that goes back to the Kelly-Day characterization of exponentiability. And Y is exponential in Locke if and only if Y is locally compact. And that was proved by Hyland, I believe it was in 78. And the third example is that cat and post, so category, the double category of categories and the double category of posets are object-wise Cartesian closed. So every object is Cartesian because this follows from the theorem. Sorry, it's exponential. But we can do better for cat and post. Okay, so let me remind you, and notationally, I'm writing this out for posets first because it's a weaker condition. And where the alpha is, where the arrows are, should be inequalities, but I'm writing out this way to make it easier for cat. Anyway, an order-preserving map is exponential in the category of posets if it satisfies the following weak factorization lifting property, which I'll call WFL. So I'm just recalling this. It says whenever you have Y less than or equal to Y prime, and you go down and you factor or interpolate P of Y less than or equal to B less than or equal to P of Y prime, then there exists a Y double prime in between Y and Y prime that drops down to B. Okay. And for cat, you have the same picture, but there's also a connectivity condition for the liftings. And it's called referred to as a Giraud-Condorcet factorization lifting condition, which I'm just calling FL, which is weak factorization lifting plus connectivity. And by the way, a little side thing, if one of the results that led to my interest in double categories, one of the results had to do with characterizing exponential objects in the category whose objects are categories and morphisms are faithful functors. And this weak factorization lifting is what it turns out to be. Okay. So the examples that you get, cat over 2 and post over 2 are Cartesian closed because you can't get any factorizations except for trivial ones. Okay, so then that's easy to see. So what you get is that the double categories cat and post are actually Cartesian closed, not just object-wise. And that's because cat1 and post1 are Cartesian closed, and you can show that the oh, that's all you need, sorry. Okay, so now I want to give an example of something, well, a little counter example. So let's consider the double category, what double slices are. So D double slice over B, where B is an object of D. D over B sub 0 is just D0 over B. And D over B sub 1 is D1 over the identity on B. And a lemma is that one can show that D over B is a gluing category whenever D is. And so as a result, you get that the double slice of cat over 2 is object-wise Cartesian closed, but not Cartesian closed. And similarly for post over 2. And that's because while you're fine on the 0, cat over 2 sub 0 and cat post over 2 sub 0, those are Cartesian closed. But cat over 2 sub 1, which is isomorphic to cat over 2 cross 2, is not Cartesian closed because you can find some factorizations that don't lift. Similarly for posets. Okay, because when you start looking at 2 cross 2, you have factorizations. Okay, so what I want to do is just mention what the properties of gluing categories are. I'm not going to go into detail on all of them, but these were the properties that gluing categories had. First of all, D0 has finite limits. And, oh, by the way, I should mention, I didn't mention it before, I was kind of suppressing. All these examples are almost all are lacks Cartesian. It turned out that actually they're all Cartesian except, and you can use the gluing, the definition of gluing category to prove it. The one example was, 2 examples actually, locales and spaces, but for the exponentiability, you get extra conditions that you need because of the exponentiability of these continuous lattices. So anyway, one of the properties of gluing categories were D0 has finite limits. The functor that takes an object of D to the identity, vertical identity on D, has a left adjoint, which I call gamma. And that the way to say that, and we saw the dual of this in Bob's talk, is that D has cotabulators. And then you define something called gamma sub 2, because there's a terminal object in a vertical terminal object, which just has the terminal object of D0 in both places. And when you glue that, when you take the cotabulator of that, you get 2 in all these cases. We denote that by 2 because we have cotabulators. So you get an induced functor from D1 to D0 over 2, and we're assuming that's an equivalence. So 2 is gamma of the identity on 1. And you also, and this holds in all those categories that I was talking about that are gluing categories, and you're also assuming that the diagrams you get by pulling back along one of the inclusions of the 1s and 2, the source inclusion and the target inclusion, give you the source of V and the target of V. And finally, that D is horizontally invariant. And it turns out that cat and post are have and top and lock all have these properties, but I'm just going to mention what the cotabulators are here. In cat, you take the objects of, so given a vertical morphism phi, the objects of gamma of v are disjoint union of the objects of x of s and x of t, and morphisms for things in x of s and things just in x of t are the ones that come from x of s and x of t, and the morphisms from x of s to x of t come from v. And this is precisely the collage of v. Okay, and similarly for posets, it's just that you have order instead of the order instead of functors. And then for top, that construction is the cotabulator of a vertical morphism. So remember, the vertical morphism is a function on the open set lattice. So gamma of v, the space, you take x of s, disjoint union with x of t, and you say u contained in there is open if its intersection with x of s and its intersection with x of t, which I'm calling u sub s and u sub t, is open, and u sub t is contained in v of u sub s. And for locales, cotabulators are given by what's known as Artin-Wraith gluing. And it's actually similar to, in fact, that's what this is for spaces. It's your really, at least the open set lattice, the open sets of gamma v, you're just doing the Artin-Wraith gluing on the v. Okay, and that's it. I'm finishing a little early. So I've listed all the papers I mentioned, if anyone is interested. Okay.
Okay, thank you very much.
Any questions?
Yeah.
Could I ask a question?
Certainly.
Thanks a lot for the nice talk. I was just wondering about your definition of these, what they're called, weak factorization liftings. Is that what they're called?
Oh, yes. What about it?
So I'm just curious to know if, is it the case, because this looks slightly like multi-op vibration, but only if, is it the case, first of all, that you can, given a beta in the base, you have a family of lifts from y to y prime prime? Is that something one can compute in the cases you have?
No, you have to have a factorization. You can only lift factorizations. Given a factorization beta for looking at cat, given a factorization of p alpha of the form beta prime, then there is a y prime sitting over b that goes down to that factorization. That's why I call Condorcet lifting or Condorcet fibration, because it's kind of like a fibration, but it's fibration on liftings.
Interesting. And it's not the case that if you had any other y, let's say triple prime, that were also a factorization in the fiber that also maps down to b, that those would have to be isomorphic of some sort?
That's what the connectivity is. So if you have say a y triple prime,
yes.
You're going to look at the equivalence relation generated by diagrams. You could go from either y double prime to y triple prime or vice versa, and then the whole thing commutes. But for posets, it's weaker. You don't need, there's no sort of uniqueness or connectivity. You can have many, many, many lifts of many things sitting in down. If you have something sitting in between P of y and P of y prime, you can have many things sitting above it. And that's true if you're looking at if you're restricting to faithful functors.
Interesting. No, because I mean that looks like 1/2 of the multi-op vibration property. It was just funny.
Yeah, it's
Interesting.
that's why it got called Condorcet vibrations, and that's because someone, I think I know who it was, but that's okay, didn't know about the Giraud result. They just knew about the Condorcet result, and the Giraud result came a year earlier, and I knew about that from my thesis advisor, who was Barry Mitchell, who introduced me to the original version that was in Giraud's work of the characterization of exponentials and cap as the ones that have this factorization lifting.
And could I ask one more question? Sorry, I don't want to take all the time, but
No, I finished early, so you're
okay. Oh, good. No, it's just maybe it is interesting in this context because you see, like when we do writing theory, we often work with topoi or other adhesive categories. And part of our axiom system for these rewriting theories is that we have a double category. Again, like I think we rotate them 90 degrees, but okay. But where the D0 and D1 have finite limits. So, and this seemed to appear also in your construct. Sorry, I forgot at which slide, but I mean, there was also a point where you have a special construction when the D0 admits.
Oh yeah,
limits.
that was for, I thought you were going back because all of these things can be done, and those first few examples can be done in a topo. So I just was restricting to sets to make it simpler.
Right.
But in let's go all the way down. In the gluing categories, you have D0 has finite limits. And the reason I have finite limits there is because, well, I want the terminal object so that I can form two.
Right.
And get this equivalence, but also I want the pullback, that this equivalence between D1 and D0/2 to come from pulling back. And that all has to do with how these things are proved.
Because that, I suppose in the more general, well, not more general case, but I mean in the case where you have an adhesive category and which is a topos, or if you have even if you have just a quasi-topos, there's this nice way of defining final pullback complements by exactly this classifying object that you essentially, for example, in graphs, you have an additional vertex and edges to it. This object 2 is presumably something with which you can define final pullback complements, no?
That's a good question.
I mean, imagine you have the double category where you take as D0, let's say a topos, and then as horizontal morphism, sorry, again, you swap them. In one direction is just the regular monos, and one direction is arbitrary morphisms. And then you can define for the final pullback complements, and you can define. Okay, maybe sorry, that would be better on a whiteboard, I suppose. Yeah, but yeah. Okay, so sorry, I'll write you an email. Yes.
You're saying that in that category, you might have all these conditions?
Yes, and I have a feeling because I do you know Wolfram Kahl by any chance?
Who?
From McMaster University, Wolfram Kahl. He's a computer scientist, and he has a paper on how to use cotabulators to define a lot of concepts in a writing theory. And I find it interesting that you have a use for cotabulators, apparently. I'll write you an email and send you the reference. Maybe I can ask them more concretely.
Yeah, I'd be interested in knowing if those are the examples, besides just Grothendieck toposes, those are all the examples I know.
Oh, okay. Yeah. Okay, maybe one could.
Those 4 examples plus Grothendieck toposes, which the cotabulators are the what are known as Martin-Raith gluing for toposes, which I then restricted that to locales way back when I was doing the constructing the exponentials for locally closed inclusions.
Yeah, it's just that I have this rough feeling that we might also have the situation that we have cotabulators.
Yeah, why don't you send me an email?
Yes, thank you very much.
It looks like Bob has a question also.
Yes, have you looked at exponentiability for double functors?
No, I haven't. You see, what happened is, as I just after your talk at in the Oktoberfest, I started thinking about. I had thought a 3 years ago about the object-wise exponentiability. And when you were talking about your abelian group, double categories of abelian groups, I realized, oh, I can just talk about this in general, because that's what you were doing. You were doing object-wise, but I was interested in the bifunctor.
Yeah.
And so I just started thinking about this a few weeks ago.
Would be nice to see sort of how the Giraud-Condorcet condition sort of doubles.
Yeah, I mean, it does for 2 categories, right? There's a 2-category version of it. But for double categories, that would be interesting. Yeah, because double categories are that's Cartesian closed, and the question is it locally Cartesian closed?
Right.
Well, it's not, but which are the exponentials?
Yeah.
Right. Thank you. That's a good. Yeah.
Other questions? I think I had 2 questions actually that I might ask you.
Okay.
The first question is this, do you know of how to construct possibly a free gluing category on a category with finite limits or something like this?
No, I haven't. I hadn't thought about that. No idea.
Because I mean,
Worth...
you're pretty much, the characterization, right, if I understood correctly, is that the category of morphisms is isomorphic to the slice of the category of objects over some 2.
Yes.
Right.
In a very specific way, but you also need this horizontal invariance.
Right.
Which basically allows you, when you have the exponentials, and it allows you to lift an isomorphism that you need, basically.
Yeah. Okay.
But no, I'd be worth thinking about.
Yeah.
But
okay, that's interesting. The second question I had was, I guess monoidal double categories are also quite popular these days, and whether you thought about closed monoidal.
Yeah, actually,
categories.
as I said, when Bob asked, I had just started thinking about this, and he was alluding to monoidal closure. And I think that some of this might go through. One could do the same thing for monoidal closure, consider a global and an object-wise thing.
Yeah. Okay.
But I haven't.
Okay. Cool. Thanks.
I don't know if things will be quite as nice, because with this exponentiability, the fact that pulling back along exponentials gives you exponentials makes things work, at least here. I don't know what happens in general. I'm looking at some other examples. For example, if you look at the opposite of the category of commutative quantiles.
Okay.
Commutative unional quantiles. And you basically do what you do with locales, where you have the horizontal morphisms or the quantile homomorphisms, the vertical morphisms are the basically the instead of preserving multiplication and unit, there's inequality, they're lax. They're order preserving maps that are lax. And the exact same construction that one does without having the isomorphism with D0 would be under, well, if you're in the opposite category, so be under basically a certain 3 element. For locales, you have the Sierpinski thing is a 3-element locale. Okay. So you don't have that isomorphism, as far as I can tell. I've thought about this many times, but I think that the construction might go through. That's what I'm working on now. So that the opposite of commutative quantiles is going to have a, I do know what the exponentials are in commutative quantiles. Instead of being continuous lattices, they're completely continuous lattices. and it might go through. And also one can generalize I'm not sure that this is what you're asking or alluding to, but you can also generalize from rel to, instead of quantile value relations, locale value relations. You can do a generalization of rel for that, and everything does go through there.
Yeah, I
Those
guess.
are the only other examples I know about.
Yeah. I mean, I guess with these examples that you've looked at of gluing categories, you also have like this. I know there's certain double functors between some of these double categories, and I assume maybe in some cases it also preserves this closure structure that you have.
You know, I've thought about that for, see if I can include the reference. No, I didn't include the reference, but I thought about that for many of these gluing categories, especially relating exponentiability for posets and top and locales in a paper. In fact, that's where I did the poset characterization. So there are relationships of when exponentials are, and for Grothendieck toposes too, are preserved or not. But I haven't thought about it for double. I think the results will probably go through since they're all gluing categories. But that's something that might be worth looking at, because there are double functors between some of these categories.
Right, yes.
Anything else?
Sorry, just to mention, I posted the reference in the chat from Wolfgang Kahl, just in case.
Let's see.
I think it might be a nice
Okay.
example.
Thank you.
And
Well,
thanks again.
Yeah, thanks. Oh, so that will be, because we're recording, I can see that in the, maybe not, but I can open it. Okay. And I lost what I was. There it is. Okay, any other? No.
Okay, well, if there's no other questions, let's thank our speaker again.